So last time we talked about the energy, is it? So we almost go through all different kinds of energy. But let's have a look at, so let's say, example 4, okay? So let's say the mass of A is larger than B, and both of them are released from rest. Then you know that it's annoying. So you know both of them will gain kinetic energy. So object A will move downwards and object B will move upwards. And then these two displacement will be the same. So let it to be x, okay? By considering the energy, the potential energy of object A decreases because it's going downwards. Object B, PE increases, and both of them kinetic energy increases. So therefore, the energy conversion is like this. The loss in potential energy of A is the gain in potential energy of B, and also the two kinetic energy. So you write down the formula, then the loss in potential energy of A will be MAG times X. The gain in potential energy of object B will be MBG times X. And then plus half MA V squared plus half MBV squared. So both object A and B have the same speed. We've learned it before because they are connected by the same string. So they will have the same magnitude of speed and also same magnitude of acceleration. Okay. I'll assume that both of them are initial at rest. If not, then you need to find the change in kinetic energy. Then that's it for this one. This one is much more complicated. I just make up the question by myself. So right now the string is in its natural length, so that means the distance between the object to the ceiling is the natural length. The string is initially is neither compressed or extend initially. So then the mass m is given a kick horizontally. So the mass m has some speed. So we want to find the minimum speed such that the ball can lift the table. So before the ball lifts the table, there is always a non-motion. When you say it lifts the table, that means it lost the contact with the table. Is the background noise that very annoying? Yes or no? I can't help. I can't help. A bit, is it? So maybe let's have a shorter lesson because then we have longer lesson tomorrow. But let me at least finish some of the example in energy. Then let's go to talk about the momentum tomorrow. If you want to find the minimum speed to lift the table, and then so let's say if you have the speed, initial speed. So just when the ball lifts the table, there's no motion. There's no motion. So that means the tension or the spring force provided by the spring will be the vertical component of it equal to the weight. Otherwise, okay, let's say if there's a non-version, then you will write something like this, okay, n equal to m plus kx cosine theta. That's a real component of the spring force that equal mg. So when it lost content, so you say non-version is 0, the mg equal kx cosine theta. Okay. Then you can write down this formula, okay, kx equal mg cosine theta. So this is condition when the object can leave the table. So you can also by trigonometry, the x is an extension of the spring. By trigonometry, you can see that cosine theta is L over L plus x. By combining these two formula, then you can say that the x equal to this one. Okay, the extension of the object equal to this one. Then by consider the energy. It loses the conversion of energy because the object is not going upwards or downwards. There's no increase or decrease in the gravitational potential energy. But when it moves to the left, its speed will decrease. So that means there's loss in kinetic energy. So this part is a loss in kinetic energy. Then it will equal to the gain in the elastic potential energy. Okay, so that is half kx squared. Okay, that's gain in the elastic potential energy of the spring. Then we just substitute the x in this formula. Then you can get the initial speed to be this form, this complicated form. Okay. You may think one more think about it. Think of it more deeply. So how about if KL equal to mg? If KL equal mg, if you look at this formula, the denominator will become 0. So that means the speed should be infinite, such that the ball can lift the table. Okay. How about if KL is less than mg? Then it means that the speed is impossible. Or because the speed you take is a positive value. It means it's impossible for an object to move to lift the table, no matter how hard you push the object. Because if you think like this, okay, when the angle, let's say when the angle is very large, so let's say close to 90 degree, then the extension will also very large. When the angle tends to 90 degree, the extension also tends to infinity. And it will store infinite amounts of elastic potential energy in the spring. So that means it's possible for the object that cannot leave the table. Okay, then let's move on. So this is a very strange example, I know, because I just made it by myself. Then let's have a look at this one, example 9. So rectangle blocks with the side A and B are placed on a rough table. Find the minimum energy to push the block from position 1 to 2. Now, although you may think that At this position, the object has larger energy than the position 2, but it still requires energy to push from the position 1 to 2. Now, for an object that is not a point, we need to consider the center of mass, the center of the object. So the center of the object at this point is this one, and this point is this one. When you calculate the mgh, the h is the height of the center of mass, or the change in height of the center of mass. Okay. At the position 1, the center of mass is not at the highest point. So at the center of mass is at the highest point when the center of mass is just above the contact point, like this one. Then this length will be, you just take the square root. This length is the length from this center of mass to the edge, to the vertex. So that will be square root a over 2 total square plus b over 2 total square, this one. So this is the largest height of the center of mass from the ground. And then, so at this position, the gravitational potential energy is largest. So what you need to do is just to provide the energy such that the object can move from position 1 to position 3. And then you just release your hand, then the object can fall by itself. And then it can become the position 2. So the amount of energy required will be the mg, and then this is the maximum height of the center of mass, and then minus the initial height of the center of mass. Then you get the change in potential energy. Okay, this one. Example 10. Okay. You need to use momentum, okay, but leave it. This one you also need to use momentum, so leave it. Okay, then I think we need to go to learn the momentum. Where's the momentum? Okay, here. I think you learn a bit of momentum in Form 3. So then let's go on. The momentum is another quantity that is conserved in some cases only. Unlike energy. So whenever you see the question, so first of all, you need to have a look whether there is a friction or not, or whether it is a cohesion or not. If there's no friction and there's no cohesion, most likely the energy will be conserved. If there's a friction, there will be some energy that's lost as friction. Then for momentum, this is another quantity that will be conserved in some case. So let's have a look how we define the momentum. So momentum can be written as is defined as mass times the velocity. So momentum is also a vector because velocity is a vector. And then if just for one object, the concentration of momentum will be just same as the concentration of the Newton's first law. So for the Newton's first law, you say that if the net force is 0, then the object will either arrest or continue its motion with constant velocity. So think it like this. So if the net force is 0, so that means acceleration is 0. then there's no change in velocity. The change in velocity is zero. If there's no change in velocity, then the velocity will become constant. Or you say that the change in momentum is zero. So that means momentum conserves. Okay? So these two laws are identical if only for one object. But if it's not one object, if there's a system consisting of more than one object, then the conservation of momentum will be useful. So let's have a look at the Newton's second law again. So Newton's second law, what you have learned for the Newton's second law is just FU_ma. But the original form of the Newton's second law is actually the net force equal to change in momentum over change in time. It's what Newton have written down originally. And then if you say that, okay, then the net force is zero, then the change in momentum will become zero. Okay? Then how about for a system? So for a system, the net force for a system is just a sum of all the net force of the system, of the objects in the system. And then we will say that then how about the P? The P will be just the sum of all the momentum in the system. So you can write it as m1 v1. This is a momentum of the first object, mass and velocity, plus m2 v2. That's the momentum of the second object. Then plus m3 v3 and so on. So if the net force is zero, then the total sum of the momentum of the in the system will be, the change will be zero. So that means it will be constant. Okay, so that is the conservation of momentum for the system. I will go to have a look at this form again in the in this page. So let's have a look at this page first. Oh, this one. So let's have a look at the case of collision. Just consider the object M1. This ball hits another ball. Now I'm not assuming these two balls have the same mass. So just let their masses to be M1 and M2. And let their velocity to be V1 and V2. So during the collision, so we need to check whether the net force is zero or not before we can apply the conservation of momentum. So during the collision, so when they hit each other, so there are forces acting between each other. Now this force is the ball 1 acting on ball 2 and ball 2 acting on ball 1. So by Newton's third law, they are acceleration pair. So they have the same equal magnitude but opposite in direction. Okay. Then if you consider the net force acting at the system, you may ask where is the normal motion and the weight? Yeah, there's normal motion acting on the object by the table and the weight, but these two will cancel out to give the resultant force zero. So if you consider the net force of the system, so we know these two forces are acceleration pair. They have the same magnitude but opposite direction. So that means the sum of these two forces will become zero. Then we can conclude that the net force of the system is zero. Okay? Then we can apply the conservation of momentum. So what does it mean? So that means the m1 v1 plus m2 v2 are constant. Also, that is the momentum before collision. So that is m1 v1 plus m2 v2 here. So this is the momentum before collision. That will equal to the momentum, total momentum after collision. So that is m1 v1 pi plus m2 v2 pi. Now you may ask, how about if I just consider one object? Now just consider m1. You know, there's a force acting on m1 when they collide. So if we just consider m1, the net force is not zero. Then the momentum of m1 is not conserved. Okay? But if you consider the system m1 and m2 together, then the total momentum will be conserved. Then we can apply the law of conservation of momentum. Then we have this formula. Okay. And remember, velocity v1, v2, v1 pi and v1, v2 pi are vectors. So that means you need to take care about the directions. So let's say if v2 is initially opposite to v1, then let's say v1 is positive, then v2 will be negative, and so on. Any question right now? Although you have learned about learning before, and this is Olympic, so we learn a little bit more. So you know forces are vector, so that means there's two directions. It can be if for the 2D case, it can be two directions. So there will be a horizontal component and also a vertical component. Then we can write the Newton's second law as like this. Also for momentum, there is a horizontal component and also a vertical component. So we can separate the Newton's second law into two components. So one is horizontal, one is vertical. Now, horizontal and vertical are always independent to each other. So what does it mean? So that means if the net force in the horizontal component is zero, if this one is zero, then the change in momentum in the horizontal component will be zero. But at the same time, if the vertical momentum if the vertical net force is not zero, then the change in vertical momentum can be non-zero. Okay, they're independent. So it can be horizontal momentum conserved, but vertical momentum does not conserve, or vice versa. So we are going to deal with these two cases later on, but just let you to have a look at it, and then we go on to have a look at some more cases in momentum. Maybe I leave this one as a homework for you today, and then you do it right now, and then send it the answer to me afterwards. Because many of the Olympic questions require you to do this kind of algebra. And I hope you are able to do this algebra by yourself. Just two formula. Although it is a bit complicated. You try to think about it to see if you can solve it. So this is always correct. Okay, this is always true. So how about energy? How about the energy in the collision? The energy in the collision may not be conserved because during the collision you can hear the sound, and also after many times of collision the object will become hotter, so there will be some thermal energy. Now the kinetic energy of the object may be converted to sound. So that means the kinetic energy, the total kinetic energy may not be conserved. But we just consider one very special case. So that is called the elastic collision. So in the elastic collision, the total kinetic energy is conserved. Now, why I say total? Because after collision, the velocity or the speed of both objects will change. If you're just talking about the kinetic energy of one object, it's never conserved. It's never constant. But if you're talking about the kinetic energy, the sum of the kinetic energy of the two objects, it may be a constant. And it's a constant in the elastic collision only. Then we can write down one formula like this. The initial total kinetic energy is half, the formula for Ke is half mv squared. Then after the collision, the total kinetic energy will be half m1v prime squared plus half m2v2 prime squared. Okay. So what I want you to do today is make use of these two equations. You may copy it down by yourself. Now, I would like you to express v1 prime, that is a velocity after collision, in terms of v1 and v2, m1, m2, and also express the v2 prime in terms of v1, v2, m1, m2. That's it. Okay, by you making use of these two equations. It's a bit complicated, but you already have learned all the skills you need to solve these two equations. Sorry, I must stop here today. I have another lesson soon. I have few tutorial for senior form.